So today we are going to actually go in and calculate a one proportion z interval. We talked about what a confidence interval was the last class period, but now we're going to actually go in and do the mechanics of calculating one and what a free response should look like. So I do want you to know we're doing lots of objectives today, but it's all going to be covered pretty nicely because the way we try to help you remember these steps for calculating a confidence interval is by panicking. PANIC. That's the what we use to remember everything that needs to be written down when you are doing a confidence interval. So the first thing you want to do is you want to define the parameter. Remember, the parameter talks about population, so you're either defining P or mu. And in our case for this unit, it's always going to be P. A is check the assumptions and conditions. You should be very comfortable with this. We've done this since sampling distributions. Same conditions are going to apply. Nothing from that is going to change. N is name the inference method. And with what we're doing today, it's going to be the same thing across the board. I is calculate the interval. And C, write your conclusion and context, which we also have done in the previous lesson. We talked about how to interpret a confidence interval. So the first thing, how do I define the parameter? Well, recall we calculate a confidence interval to give an interval of plausible values for an unknown population parameter. So we have to say, what is it that we are trying to describe? And for us in this unit, it's always going to be proportions. It's always going to be P. So we will say P is equal to the true proportion of blank. Whatever the question is asking, whatever the context is, whatever your parameter of interest is, that is what we state. We have to define P before we go in and create intervals. Next thing we're going to do is check assumptions and conditions. Randomization, 10%, success, fail. All of this is the same from sampling distributions. The only difference is in my success fail condition, typically it was n times p is greater than or equal to 10, n times 1 minus p hat is greater, or p is greater than or equal to 10. But notice that in this problem, they are not p's, they are p hats. And that's because with confidence intervals, you are trying to estimate P. You don't know what it is. You're not given an approximate value of what P could be. You're trying to figure that out based on a sample. So the only proportion you have when you're doing confidence intervals is P hat. So we will use P hat for this success fail condition only when we're doing confidence intervals. Now, next you're going to name the inference method, and this is what you'll state every single time you're doing a proportion confidence interval, one proportion z interval. And z is going to come from the fact that we are going to be using the z distribution to calculate our probabilities. So one proportion z interval, and you'll say this every single time, you have to name the test in order for them to give you credit, especially if when we get to that point, you're switching to calculator versus by hand. They will absolutely require seeing you name what inference method you are doing. So we've done PAN. I is the actual calculation of the confidence interval, and we've talked about this briefly yesterday, where we said it was the point estimate, which is your sample statistic, plus or minus the margin of error. We talked about how on the formula chart, it says statistic plus minus critical value times standard error of statistic. But the actual calculation you are going to use for one proportion confidence intervals is P hat, your sample proportion, plus or minus z star, which is going to be a critical value. It's a z-score that tells us the cutoff points for our shaded probability region, times square root of p hat, 1 minus p hat, all over n. And again, this standard deviation formula that we're used to seeing is almost the same. The only difference is it's p hat and not p. So we call it standard error and not standard deviation, just because it's calculated based on p hat instead of the true proportion. And again, this is how it appears on your formula chart, but you just have to kind of plug in the different concepts from the question. Now, how do we calculate a critical value z? Well, the nice thing about proportions and the nice thing about confidence intervals for proportions, if you calculate these once and you remember them, you don't have to do it over and over again because they're not going to change. A Z star, a critical value for a 95% confidence interval, is going to be the same thing every single time. It changes a little bit when it comes to means, but for proportions, if you can remember what they are just off the top of your head, you should be fine. Now, if you forget, there is a way to calculate what the value of Z star is. So it's going to come from our kind of Z distribution processes, where if I know I have 95% in the middle, that means I should have 2.5% in this left tail. So, because again, this whole thing adds up to 100. If there's 95 in the middle, there should be 5% in each split between each tail. So this leaves me with 2.5%. Well, I can get this z-score value by using a function in my calculator, and it's called inverse norm. So I can go into my calculator and I can do z star is equal to inverse norm of area is 0.975, because I have to add not only the 95%, but this 2.5% in the tail. So I get 97.5. Mu is 0, standard deviation is 1, because we're working with z-scores. When I plug this into my calculator, I should get z star is approximately 1.9600 after rounding. Now, if you are calculating this in your calculator, you only have to do one, because they are the same value, just one is negative on the left-hand side, one is positive on the right-hand side. So this is negative 1.96, this is positive 1.96. And if you need a refresher on how to get to inverse norm, remember it's second vars number 3. And it should give you a prompt for area, 0.975. I'm going to leave 0, 1 alone, and I'm going to paste. And it should give me my 1.96. Now, if you can remember that for 95% confidence interval, Z star is always 1.96, that's absolutely fine. This is just a way to go in and remember. You can have your calculator help you along the way. I did the same thing for 90%. If it's 90 in the middle, that means there's 5% in my left-hand tail. I did an area of 0.9501. Z star is approximately 1.6449. Same thing for 99%. I did 0.5% in the left tail. Z star inverse norm of 0.995. Z star is approximately 2.5758. And I did these three because they are the most common. These are the most common confidence levels you will calculate. So I want you to at least have them written down somewhere so that you don't always have to go back and recalculate it. Sometimes it's quicker to just put it in your calculator than it is to find your notes. So whatever works best for you. These are probably the three that we will be using throughout the unit, throughout the rest of the year. But sometimes especially using MyLab, they like to switch it up and do weird confidence level calculations. All you have to do is go into inverse norm, plug in the area that you are interested in. And again, quick reminder, if I happen to be going too fast or I happen to be scrolling, I will always post my completed PDF at the end of the day. Z star for the last one is 2.5758. For 95%, it's 1.96, 90%, 1.6449, and for 99, 2.5758. I'm going to go ahead and turn off my camera. That might help it a little bit, just for me not being on screen and taking away internetness. And I haven't really written anything down yet, so just kind of showing you what's on your paper so far. Okay, next thing we're going to do is write the conclusion in context. It's going to be exactly what we did in 6.1. We can be blank percent confident that the interval from blank to blank captures the true proportion of whatever we are talking about. Now, one thing that I want to highlight here and say that is very, very important is you have to say we can be blank percent confident. Confident, the word in your conclusion states that you followed this process for creating your interval. You can't just say we can be 95% sure, or we're 95% certain, or we know that 95% chance. It has to be the word confident, because that signals someone, your grader, more importantly on the AP exam, that you have done the process for a confidence interval. This is following this procedure, and that's the only way that you can make your values have any meaning, is they have to know you went through and created a confident interval using the general process. You can't just say probability, you can't just say sure, you can't just say certain. It has to be confident. Okay, so we've kind of gone through the process, PANIC. Now we're going to actually apply it to a problem. I have Miss Contreras' AP Statistics class took an SRS of poker chips from a very large container and selected 37 blue chips and 63 red chips. Calculate and interpret a 90% confidence interval for the proportion of blue chips in the container. So, first thing I'm going to do is I'm going to start with P, which is define the parameter. So I'm trying to find the true proportion of blue chips in the container. So my first step is going to say P is equal to true proportion of blue poker chips in the container. Now I will make a note. The AP College Board graders are very aware of what panic is. If you write panic on your paper, they're not going to think you're freaking out. It is totally fine to write it out if it helps you remember everything that needs to be written down. It's okay. I know I have some students who are like, should I write it down? Are they going to think it's weird? They know what it means. They know where it's coming from. So P is the true proportion of blue poker chips in the container. Make sure you are careful and you are using P and not P hat, because we are talking about the population, not the sample. A is something we have done before. We're going to go through and we're going to check our assumptions and conditions. The first one is always random. I have taken an SRS of poker chips, so I'm going to say SRS stated. And one other thing, if you happen to do this not in linear order, not one right after another, that does not make it wrong. So if you happen to check conditions first before you defined your P, they're not going to say, oh, they went out of order, everything is wrong. As long as it's on your paper, they will grade it. I just like to do things linearly because it helps you guys develop patterns and remember what you have to do. So, 1, random SRS stated. 2, I need to take my sample size and multiply it by 10. Well, I don't have an official calculated sample size, but I can say I have 37 blue chips and 63 red chips, so that should give me a sample size of 100. So N is equal to 100. So I'm going to use that to write my next condition. Assume at least 1,000 poker chips in the container, which we can because it's a very large container. So we're going to assume that there's at least 1,000 in there. This is the 10% condition. Third one is going to be our success fail. So I don't necessarily have to go in and do 100 times 0.37 or 100 times 0.63 because we're given our counts. We're given the fact that we have 37 blue chips. We're given the fact that we have 63 red chips. So I can just use those values to plug into my N times P hat, N times 1 minus P hat, and say that 37 is greater than or equal to 10 and 63 is greater than or equal to 10. So with both of these having at least 10 successes and 10 failures, I can say it's approximately normal. This is important because this allows us to go in and use that Z star critical value to figure out what the margin of error is. So we've done P, we've done A. N is really nice because for questions like this, it's the same thing every single time. Our method is 1 proportion Z interval. And generally with the mechanics of the test, this first part usually counts as like half of the FRQ. 1 to 2 points, typically depending on whether they grade it as 3 or 4. If it's 4, typically this is 2. If it's 3, this might be 1. The interval is usually a point in itself, and the conclusion is usually a point in itself. Just depends on how they decide to break it down each year. They decide to change it almost every year. So I have P, I have A, I have N. The next thing I have to do is calculate my interval. So first thing I want to do is remember what my formula is. P hat plus or minus Z star square root of P hat 1 minus P hat all over N. So I know that I'm trying to estimate the true proportion of blue poker chips. So my P hat, my sample, should be the number of blue poker chips that I have that I selected. So I'm going to go ahead and fill in 0.37. And you do want to work in proportions. Working in percents or whole numbers tends to get confusing. Change it to a decimal, 0.37. Now, Z star, we can reference back to what we just did in calculating Z star values. We are doing a 90% confidence interval. So when I'm doing a 90% confidence interval, my Z star value is 1.6449. So I have 0.37 plus or minus 1.6449. And now I'm just going to take my P hat of 0.37 and my sample size of N and plug it into the standard error formula. 0.37 times 0.63 all over 100, take the square root of that. And from here, it's calculator work. Plug in the plus version into your calculator, plug in the minus version into your calculator. What I sometimes like to do is I like to calculate the right-hand side by itself, just so that I can see what the margin of error is. This second half, the 0.0794, is my margin of error. Just in case they throw a question at you that asks, what is the margin of error? Just calculate the second half of the confidence interval. That's all you have to do. So my interval should be from 0.2906 to 0.4494. Now, the interpretation is going to be exactly like what we did in 6.1. We can be 90% confident that the interval from 0.2906 to 0.4494 captures the true proportion of blue poker chips in the container. And I'm going to give you a little bit of time to write down if you're catching up or letting your screen decide it wants to play friendly and let you see. But most of what we are doing in this confidence interval is stuff that we covered in 6.1, prep work to be able to go in and calculate it correctly. And everything that you see and everything that we've written down so far is what is expected in a full FRQ answer on the AP exam. I can guarantee when we take our test on this unit, when we come back from Thanksgiving break, you will have one of these problems on the test. So make sure you get comfortable with the process and that you kind of know what you're doing, just so that you don't happen to miss it. So I'm going to scroll a little bit. Ms. Contreras claims that at least half of the chips in the container are blue. Do you agree or disagree with her claim? Well, half is 50%. So she's saying at least, or I'm saying, at least 50% of them are blue, meaning 50% or more. But if we look at our confidence interval is from 0.2906 to 0.4494. And my confidence interval tells me that somewhere in between these two numbers is the true proportion of blue chips. And 0.50 is not between these two numbers. So that leads me to disagree with myself and say the entire confidence interval is below 0.50. There are no plausible values to support the claim that at least half of the chips in the container are blue. So because my confidence interval does not contain the value that I am claiming, I can't agree with it. If it happened to have 0.50 in there, then I would say yes, I agree, because that is one of the possible values for this proportion. But because 0.50 is not in my confidence interval, I have to disagree. And our last little bit on confidence intervals is going to be how to do this in your calculator. Yes, the algebra way works every single time, and I will say there are instances where the algebra way is better, especially with proportions, because your calculator is going to keep throwing errors out at you for a reason. But there is a way to do this in your calculator that saves you a bit of time. So first thing you want to do, I'm going to go ahead and open up the calculator steps so you can kind of type as I talk. You're going to go to stat. So you should on your calculator have a stat button, which I'm going to try to open both of these at the same time. Let's see. There we go. Oops. Okay. So you should have a stat button. It's right underneath delete, right next to the left-hand arrow. You're going to click stat, and you're going to go over to tests. So we're in the third column, and you're going to get tempted. They have a lot of things that look like what you want. Now, they do work. Some of them work a lot with not as much ease as the one that we're going to use, because they're going to require some calculations for standard deviations and things like that. And you don't want to have to do that if you don't have to. So I'm going to go down instead, and I'm going to skip over one prop or Z interval. I'm going to skip over all of that, and I'm going to go to A. A says one prop Z it. We have one proportion. This is a Z interval. This is the one that you want. Letter A. Now, it's going to ask you three things. It's going to ask you X, which should be the number of successes, N, which is your sample size, and C level, which is your confidence level. So our number of successes in our sample, we had 37 blue chips out of 100. And we want to calculate a confidence level of 0.90. So I'm going to hit calculate, and it's going to tell me my confidence interval is from 0.2905 to 0.4494, which is exactly what we calculated by hand. Almost. Rounding sometimes gets a little bit off. Now, one thing, it's great, it's lovely, the calculator works. However, often in your proportion confidence intervals, they give you a percent rather than a count. So they'll say, oh, about, it's not going to work for poker chips, but they say sometimes like 63% of the sample has a cancer or something. Can't think of an example right now. But in that instance, they give you a percent and not a value. So if I were to go back to stat tests and I were to go down to A, and say, for instance, when I do that calculation, so say I had 243 and I multiplied it by 63%, because that would be my sample, and I'm going to change my sample size to 243. Notice that when my calculator does the X, it gave me a decimal. So when I go down to calculate, what your calculator is going to tell you is error. If you do not have a whole number as your X value, it will always give you an error every single time. So be careful with that. Make sure, I always suggest rounding up. That's generally the rule we do in statistics, especially if there's even a little bit of leftover room. They'll have a window large enough on the grading rubric to accommodate for that. So x must always be a whole number. One thing you do want to note when you are doing work in your calculator, write everything down after you calculate. Write everything that comes out of that output window, the interval, p hat, and n. And this here would fill in the place where you're calculating the confidence interval. So that would just go there instead. Everything else should stay exactly the same. You should still have the P, the A, the N, and the C. It's just this would be your calculation for confidence interval. Now, let's go ahead and get to the last little bit of content. Calculating a sample size and confidence level. This is all going to be mostly algebra, plugging in things to a formula, figuring out what's missing. I have my margin of error formula is z star times standard error, p hat, 1 minus p hat, all over n. My example is a pollster is hired to determine the percentage of high school students that are in love with spicy food. If we require 99% confidence that the estimated value is within at least 2% of the true value, how large should the sample be? Well, being within at least 2% of the true value, that tells me my margin of error is 0.02. 99% confidence is a z star of about 2.5758. And that's just from our calculations on page 2. And when we're not given a P, we're going to assume P is equal to 0.50. And in our case, it's more interchangeable, P and P hat, just depending on what information they decide to provide you with. This one didn't provide us with the sample or it's not going to provide us with the sample, so we're going to have to work based off of a true proportion. So I'm going to plug in what I know. I know margin of error, 0.02. I know z star, 2.5758. And I know P is 0.50. So 0.50 times 0.50 all over n. Now, notice that I changed it to a less than or equal to. When you are doing margin of error, you can always have a smaller one because that's ideal. The goal is to have the smallest margin of error possible so that you can be really close to the true value. I don't want to say that this value is going to be larger than my margin of error. So you can always set it equal to each other. Typically, it's going to be a question of which of these sample sizes would give you this margin of error. And it's a multiple choice question, and you pick the one that's closest to your answer. But I usually do margin of error is greater than my statement. So from here, I'm going to go into the algebra steps. I will say if you are doing this in your calculator, I highly suggest just leaving it unrounded. I'm going to show you how big of a difference we're going to get when I start rounding values and when I use the unrounded numbers. Now, you do not have to do all the algebra written down. I'm writing it down for the people who want to see how we get to our final answer. But if you know how to solve for n and you know what n is, perfectly fine. So the first thing you're going to want to do, I want to get n by itself. So I'm going to divide on both sides by 2.5758 because that's going to get rid of that coefficient. So this gives me, and this is a rounded number, approximately 0.0078 is greater than or equal to square root of 0.25 over n. The next thing I want to do is I want to square both sides to cancel out my square root. This gives me approximately 0.00006084 greater than or equal to 0.25 all over n. And with some reciprocal magic, some fraction work, I would multiply by n, but then I would divide by 0.006084. So that gives me n is greater than or equal to 0.25 over that really long decimal. And from here, you just calculate. You need at least 4,110 people to have a margin of error of at least 0.02. So first you divide, then you square, you do some reciprocals, and it's just a calculation. Now, I would not write this down and round it personally, because I'm going to show you in my calculator. Let's get out of this error. I'm going to do this as I would in my calculator. So first thing I have is 0.02. I'm going to divide it by 2.5758. I'm just going to calculate that. I'm going to take my value, which I did round, and I'm going to square it. And I'm going to hit enter. This is my decimal, which I did round mostly, but it's really, really long, and I want to use exact values as much as I possibly can. But now I know I just need 0.25 divided by this number. So I'm going to do that. Alpha y equals 0.25 divided by my second answer. And then I'm going to press enter. When I do it in my calculator only, I get a sample size of 4147. That's a big difference between the rounded version and the non-rounded version. So I always recommend doing it in your calculator. For the most part, your answer choices will be so far apart that it won't seem like a big difference because you'll have varying values. But just in case you have two things that are really, really close to each other and you're not sure which one to pick, always verify in your calculator just so that you can kind of make sure you're doing the right thing. So, highly suggest using unrounded values in the calculator. Last and final thing, a TV news reporter says that a proposed constitutional amendment is likely to win approval in the upcoming election because a poll of 271 likely voters indicated that 53% would vote in favor. The reporter goes on to say that the margin of error for this poll was 2%. What confidence level did the pollsters use? So this time we know margin of error, we know sample, we know what the P is. We just need to figure out what confidence level did they use. So first thing I'm going to do, I'm going to identify some things that I know. Margin of error. We don't know what Z star is in this case. We know N is 271. And we have a P hat. We have a sample that indicated 0.53 are voting in favor. So I'm going to take all of those values and I'm going to plug them into my margin of error formula with what I know. And again, I'm going to walk you through the algebra version, and then I will walk you through how to do it in your calculator. So the first thing we're going to do, and really the only thing, the easiest thing to do, is Z star is being multiplied by this entire square root. This square root is just a number. There's no variables in it. There's nothing you have to solve for. So what I do is on both sides of the equation, I divide it by square root of all of those numbers. And that gives me Z star is approximately 0.6597. Now that is not your final answer. Can I guarantee that they might put that in there some way, somehow? Yes, it usually will be an answer choice just so that they'll kind of trick you into thinking that you are correct. Z star is a Z-score. These are the cutoff values of my area that I am interested in, of my confidence level area. Now, I can use these two numbers to estimate what the confidence level should be because I'm just trying to find what this area represents. And we've done that before. We've done it using something called normal CDF. My lower bound is negative 0.6597. My upper bound is 0.6597. Mean is 0. Standard deviation is 1. And we get approximately 0.4906. So this leads me to believe they have a very, very bad confidence level of 49%. Very low. Something I wouldn't necessarily put a lot of faith in if someone's only 49% confident that their interval is capturing the true proportion. So, again, just a reminder of calculator steps. This one isn't so bad. This one isn't too far off compared to the other one that we just did. I'm going to move it to this side just so you guys can see it a little bit better. You can keep writing while I'm working. I always say alpha y equals is the easiest way to do this. Put a fraction bar in your calculator, 0.02 over square root of alpha y equals. Again, I have 0.53 times 0.47, because that's 1 minus 0.53, all over my sample size of 271. And this one's pretty close to what I rounded off as my value, 0.6596 or 97. If you want to store a value so that you don't have to round it at all, once you've calculated it, if you hit the STO arrow button and you put a variable, so we're going to store this number in variable X, it will make it, every time you type in an X, it's going to give you that number. So that's like what I typically do. I'm going to go second vars, normal CDF, negative X to positive X gives me approximately 0.4905. So I'm a little bit off, but not by much. Calculator one still rounds out to be about a confidence level of 49%. So today we are done. You're almost on break. I do want to go over what's posted, what's getting posted. You technically do not have to do anything for Thanksgiving break.